Hello, everyone. My name is Kurt Schultz. I'm a graduate student here at Fresno State in the physics department. I'm doing research with Dr. Frederick Ringwald. We are doing research in a field of astrophysics. Namely, my research is focused on classifying cataclysmic variables from the large-scale synoptic surveys that we get from automated telescopes. And the reason this is important is because in the future, in the near future, we will have even more capable automated telescopes. So we're going to get some just waves and waves of data, and we need a way to analyze the data fast and efficiently. So let's go through here. So again, my research is focused on cataclysmic variables, and that's what this illustration here kind of depicts. So a cataclysmic variable is an attached binary star system. So typically we have a primary white dwarf in the middle of this area here. And what is happening is you have a secondary star, which is it's very close in proximity. So it's actually transferring mass from that star onto the white dwarf. And what happens is due to conservation of angular momentum, an accretion disk forms. So that's this disk we see here. And at the point of mass transfer, we have this spot, which is known as a hot spot. And what happens is, since that's such an energetic area, energetic spot, it flickers. So it's very intense in light. And since there is a non-uniform distribution, transfer of mass, for example, mass goes in a lot at once or goes in a steady stream, but the idea is it's turbulent, it's chaotic. We don't really know how it actually enters. And what happens is that spot flickers, okay, because of this non-uniform mass transfer. And that flickering actually follows a nonlinear mathematical modeling known as self-organized criticality. So the idea there is that the very large infalls of mass correlating to peak intensity, they happen much more rare than the lower infalls, than the lower mass transfer rates. And therefore, what we have is very rare large events and fairly common lower events. So that is kind of what dictates self-organized criticality. A good example of that would be like an avalanche. That's kind of the quintessential example. So think about avalanches occur very often, but we only observe the very large avalanches rarely. So that's kind of the idea. Anyway, so what I'm doing is I'm taking that flickering, which kind of looks like noise, and I am applying a certain algorithm to it to determine how noisy it is and if this is the type of noise that comes from a cataclysmic variable, because it is very unique to cataclysmic variables. Few others show this kind of noise. So this next column here, what we start with is different types of noise. And so mainly what we're focusing on here is the first one. This one correlates to completely random. And the second one, which actually does give us some information. So if you go all the way to the bottom of this column, you'll see that I do have an illustration of a time elapsed reading from a cataclysmic variable. And you see that it does, goes up and down. It flickers like that. And you can also notice that this, if you look at this reading and look up here, it kind of fits in between the first two, which would be white noise and pink noise. So the idea here is an event like this in self-organized criticality, you can create a power law plot. So what you do is you take the intensity of light, take the log of that, and that goes on the y-axis, and the frequency, the log of the frequency of the events goes on the x-axis. And what you're supposed to get, if it is self-organized criticality, is a nice line. So in this case, the reading we get is already logarithmic in nature, so we don't have to take the log of the intensity, its apparent magnitude. And also, the data we get from automated telescopes is not time resolved, so we have to find a different way to analyze that. So what I did is I just ranked all the measurements. So when I did that, I actually did come up with something like this on the third column here. And I do have a line, and it does have an identifiable slope. So I did that for roughly 40 known cataclysmic variables, and I did it also for a bunch of different astronomical objects like galaxies, variable stars, other things like that. And what I found is that I have this kind of a correlation. So you see the slope for the cataclysmic variables is around here. It's an average of about 0.3 to 0.4. And that's for cataclysmic variables. And for non-cataclysmic variables, it's much lower. It's on the order of pretty much between 0 to 0.1. So there's definitely a correlation there. And this is a method that can be used to classify cataclysmic variables from just raw data. I also looked into histograms as data analysis. And what I found there is if you look at something like this and you find multiple maxima, it can tell you that that might be a detached binary. Right, so the idea of my research is that we need to keep up with technology. So since we'll be getting a lot of data in a short amount of time, we need to be able to crunch that data. Thank you for listening.